All right, so in this video, we're going to go over a generalized autoregressive conditional heteroscedasticity model, also a GARCH PQ model, so order of P and Q. And this is basically just running an ARMA model, an autoregressive moving average model for the variance of the error. And then for this, as mentioned in the slides, typically, especially in a lot of finance applications, you can just do a GARCH 1-1 model. So that's what we'll do for a lot of our examples. We'll still go over a generalized GARCH model, but we'll mainly focus on the GARCH 1-1. So anyway, so for this, for a GARCH 1-1, GARCH 1, 1, we're going to get the variance. Remember, this is the second moment of the error term, so error expected value of the error term squared. Anyway, so the variance at time t is going to be equal to our w plus alpha times the one lag of the error term. So it's GARCH 1-1. So one lag of the error term squared plus beta times one lag of the previous variance. And just like in the arch, our error term is equal to standard deviation multiplied by ZT, where ZT is follows a standard normal distribution. And something specific for this, so like before, all the alpha terms had to be equal to or greater than 0. Same thing with this, because again, we're measuring variance, but specifically for this, alpha plus beta. So the sum of the coefficients, excluding the W, has to be less than 1. We'll go over why that is. If you remember last semester, we briefly went over the JP Morgan risk metrics model. This is a special case of a GARCH 1-1 where alpha and beta are equal to 1 and the W is equal to 0. Anyway, we'll go over the GARCH in a more standard, in a more normal situation. So let's look at the expected value. The expected value of our variance is going to be equal to the expected value of W, which is W. Expected value of a constant is just a constant. And then the expected value of our error term squared. We can factor out the alpha and we get the expected value of our error term squared. Plus, again, same thing, factor out the coefficient. We get the expected value of variance. So just like before, remember, we are assuming that we have the same assumptions as the arch model. So this would mean the expected value of variance would just be variance. The expected value of our error term squared would be variance. The expected value of, again, variance is going to be variance. So now we can factor out, we can move everything over to the left with variance, we can factor it out, and we can find the long-term variance. So this would mean that in the long term, variance is going to be equal to W divided by 1 minus alpha minus beta. This is why alpha plus beta has to be less than 1. If it's equal to 1, then that would mean this would be undefined. And if it's equal to 1, then this would be undefined, and then you can't accurately estimate the variance. So using GARCH is common in risk management for forecasting future variance. So let's look at forecasting tomorrow's variance. I might clear this. We're going to plug it into a new one. Again, we're doing a GARCH 1-1 model. So for a GARCH 1-1, we know that we're going to estimate tomorrow's variance. Maybe this would be for value at risk, or maybe it's for pricing an asset. And we get W plus our alpha multiplied by the previous error term, which would be today's error term, plus beta multiplied by today's variance. And then since our variance is equal to W divided by 1 minus alpha minus beta, we can plug this in. We can replace our W or omega, or whatever that is. So we'll plug it in. This would give us the long-term variance multiplied by 1 minus alpha minus beta plus our alpha multiplied by today's error term squared plus beta multiplied by today's variance at time t. So now we'll put this in. This would give us, let's go ahead and subtract this. So this would give us our variance minus alpha variance minus beta variance. We can combine the everything with the coefficient of alpha. We can combine everything with the coefficient of beta, and let's subtract the long-term variance from both sides. So this would give us, draw an arrow for the next step. This would give us tomorrow's variance minus the long-term variance is going to be equal to alpha multiplied by, this would be this would be the today's error term squared minus the long-term variance plus beta times today's variance minus the long-term variance. So if we take the expected value of this, we can get some some more. So we can learn more about the volatility of the specific process. So what makes one of the things from this where we can apply this, what makes GARCH specifically different than ARCH? Not only do we of course have previous variance terms, and it's an ARMA instead of an AR. Shocks to the time series. Shocks to the time series can of course affect the variance, but that would be included in the model. So something like what happened recently with COVID-19, or something what happened back in 2008, that increase in volatility would stay in the model, and eventually it will go away. It still converges to the long-term variance, but you can kind of see that persistence in a GARCH model, and you can actually have a numerical value associated with that persistence in the time series that you're measuring. So something like COVID-19 and this increase in volatility, you can see that in a specific process, and you can get that persistence. Maybe you can know how long this will affect your volatility estimates. So we have this. Let's take the expected value. So we take the expected value of our error term. I'm sorry, not of our error term, of our variance. And let's do k many days in the future. So let's forecast volatility k many days in the future. So k many days. So let's look at the expected value of variance of t plus k. So k many days in the future minus the long-term variance. This would be equal to alpha multiplied by the expected value of our squared error terms plus k many days, but it's the previous term. So it would be k minus 1 minus our long-term variance plus beta multiplied by in this expected value of our variance of the previous day, which would be k many days minus 1 minus our long-term variance. And something that we've found from before, we know that the expected value of our error term squared is going to be the variance. So these two are actually the same, so we can combine it. This would give us alpha plus beta alpha plus beta multiplied by the difference between the expected value of our error term, of our variance of k minus 1 days into the future minus the long-term variance. So this right here, alpha plus beta, this would be the persistence. This is the persistence, and as long as alpha plus beta is less than 1, then shocks will have an impact. But as t as time goes on, as t gets large, as t goes to infinity, and as long as there's no new shocks, then it will converge back to the long-term variance. However, if alpha plus beta is equal to 1, then the variance is undefined and shocks would last forever. Then one more step. I'll write this down. This is the persistence. One more step would then be factoring, taking this another step further, alpha plus beta. And again, this is in every single iteration of our model. So this would appear k minus 1 times. Then this would mean that if we take that out, you can predict, you can forecast volatility k many days in the future just based on the persistence and the today's error term, or today's forecast. So based on today's forecast, or tomorrow's forecast, you can forecast k many days into the future, as long as alpha plus beta is less than 1. So in the next video, we'll go over testing for GARCH and applying it. Then that would be it for volatility modeling, other than the Python portion.